Hey, this is Mr. Ed, and we're going to be dabbling our little pinky toes into the world of calculus by talking about differentiation. And what we're doing, we're not just going full into what's called the derivative or differentiation. We're going to kind of logically progress into the definition of a derivative, and we're going to do that by first taking a look at what's called the estimating the rate of change from a table. Estimating the rate of change from a table, and we're going to see how this kind of progresses into the beauty of calculus. And so what are we going to talk about today? We're talking about what's the rate of change, okay? And we've talked a little bit about the rate of change before. The rate of change is a fancy term for the slope of a line, right? The change in the y over the change in the x. How your dependent variable is changing with respect to your independent variable, okay? And in calculus, we're going to kind of change this delta, this triangle, to a d. It's the same thing, the delta y over the delta x, the change in the y over the change in x, and we call that the derivative, okay? And so we're going to take a look a little bit at a real-world problems here, and so we can kind of move ourselves into this calculus concept. So first, let's take a look at a real-world example of time and distance, And so we're going to take a look at a race, okay? And at 0 time, at 0 minutes, obviously the person has run 0 miles, okay, in this race, this so-called race. Well, guess what? 1 mile later, we figure out that this person has run 7 minutes exactly, okay? And at the 2 mile mark, we are timing the person. The person runs 15 minutes correctly. Exactly. And then at the 3 mile mark, at the end of the race, they've run 21 minutes and they did pretty good in their race. Now, this is our x value, our independent variable. This is our y value, our dependent variable. And so let's say this is not giving everything that's happening in the race. This is just giving a snapshot at each mile of what's happening. And so think about it. We don't really know exactly what's happening at half a mile, okay? At 0.5 miles. We don't exactly know what's happening, but we can find out the rate of change, the average rate of change at half a mile. And how can we do that? Well, we take our independent variable change. We have 1 mile minus 0 miles over 7 minutes minus 0 minutes, which means this person is running 1 mile for every 7 minutes. That's their rate, their average rate of change, or 7 minutes per mile, okay? But I'm going to kind of put distance over time, and this is called their speed, right? Their distance over their time. Now, that is just an estimate of what's happening at 0.5 miles. Can I estimate what's happening at 1.5 miles? At 1.5 miles? Sure, but I'm not going to take from 0 to 2 because that wouldn't be a good snapshot of what's happening at 1.5. The best estimate would be to take my 2 miles minus my 1 mile, this interval right here, over 15 minutes minus 7 minutes, which means this person's running 1 mile for every 8 minutes. This person is running a little bit slower, aren't they? And so we can estimate at 1.5 miles, they're running a little bit slower than at 0.5 miles, okay? And so this, remember, this is just an estimate, isn't it? Well, can I estimate what's happening at something like 2.5 miles? 2.5 miles. Well, yeah. How would I estimate what's happening at 2.5 miles? Well, I'm going to take my 3 miles minus my 2 miles. I'm going to take this interval here, my 21 minutes, minus my 15 minutes. And so I end up getting 1 mile in 6 minutes. What's happening to this person's speed at 2.5 miles? Well, they're running much faster, aren't they? Because we know what's called the average rate of change. And so this person is running 1 mile for every 6 minutes. And we can do that in so many different scenarios, like this one. We have the grain being added to a silo. At time t, that's our independent variable, is x. we know the rate, which means we know the y. Now remember, this is already a rate, isn't it? How do we know it's a rate? It is some unit per time, isn't it? So it's already a rate. This is already a slope here. So we're actually taking a look at the rate of the rate, and that'll make a little bit more sense in just a second. Let's say I want to know the rate of change, the average rate of change at 3 minutes. At 3 minutes. Well, am I going to take from 0 to 8 to find out 3 minutes? No, I'm going to look from this interval of 1 to 5. That's the best way to find the rate of change. And so I've changed 20.5 cubic feet per minute. Remember, keep your units. Minus 15.1 cubic feet per minute over 5 minutes minus 1 minute. This is the best way to find out what's happening on average at 3 minutes. So I take 20.5 minus 15.1, so 20.5 minus 15.1, and I get 5.4 cubic feet per minute over 4 minutes. And I finish this out, I divide by 4, and I get 1.35 cubic feet. Now look at your units per minute. So that's per minute squared. It's very similar to acceleration. We actually found the rate of the rate here. And this is what's happening, the best we can surmise, at 3 minutes. This is the rate of change at 3 minutes. Let me give you one more example. Let's say we want to find the rate of change at 1 minute. Okay, for this, we have the depth of water in a tank. We have inches, and it's changing per time. So let's say we want to find at 1 minute, what's the rate of change? Well, to find 1 minute, am I going to do from 0 to 10? No, I'm going to do from 0 to 2. That's the best way to find 1 minute. So I have 10 inches minus 3.5 inches over 2 minutes minus 0 minutes. And so I have 10 minus 3.5. That's going to be 6.5 inches per 2 minutes, which ends up becoming 3.25 inches per minute. That's the rate of change at 1 minute on average. Now let's say we wanted to find what's happening at 6 minutes. I'm going to do this interval from 5 to 7. So I have 18.5 inches minus 15.5 inches, 7 minutes minus 5 minutes. And so we have 18.5 minus 15.5. That ends up becoming 3 inches per 2 minutes, or 1.5 inches per minute. Now compare that to at time equals 1. This is filling up slower, isn't it? Because at 1 minute, on average, it was filling up at 3.25 inches for every single minute, this water tank. But at 6 minutes, it's only filling up at 1.5 inches per minute. And so we are able to find out the average rate of change over an interval. And this is our next step in getting closer and closer and closer to what's called the derivative.